Thank you so much once again. We are awfully punctual this year, so let us continue as advertised. It is 5:30 and it's time for our last talk of the day and another keynote speaker now, Jason Turner. Now, Jason has 2 decades of C++ experience and is a developer, trainer, and regular conference speaker. Jason created his C++ weekly YouTube series in 2016 and has released an episode every week since then. So let's have a look. Here's a high-quality screenshot of his YouTube production. Disclaimer, pixelosis has been intentional. So I give to you Jason Turner.
Thank you. Thank you. So is constexpr really zero runtime cost? And what's funny is, as I was putting these slides together, I couldn't remember what title I was going to give the talk. So then I ended up with this, the runtime cost of using constexpr. Anyhow, so yes, my name is Jason Turner. I am host of C++ Weekly. I have been publishing since March 2016, like you said. 456 straight weeks, which anyhow. Oh, of course, you can scan the QR code. If you're not currently a subscriber, like and subscribe. You know the deal. I am author, C++ best practices, C++ 23 best practices, and some puzzle books that I also mentioned in the intro thing here. And you can check out those links if you're so inclined. Developer, I've got, GitHub and all this stuff as well. Microsoft MVP since 2015. I do training, just so you know, kind of have to let you know who I am. I love doing training, and I am happy to come on site to your company. I have been to at least those countries, and I think I'm forgetting something. Yes, Canada. I forgot to put Canada on there. Or otherwise, you can come to conference workshops. Now, this isn't just a sell for me, just for the record. All of these great conferences offer workshops, and if you have any interest in getting any kind of formalized C++ training, I do suggest that you come to one of these conferences and come to a workshop. Right, Phil? OK, very good. So about my talks in general, avoid sitting in the back. Room's a little tight, so you can free to shuffle forward. I saw you waving in the back row. Yeah, you can. There's a seat right here if you'd like to come. He's actually moving down. Do interrupt me and ask questions. Yell things out. I will repeat it for the room. This is not a hold your questions until later kind of talk. In fact, it'll go far too fast if you do, so please don't. And this is approximately what my training days look like if you're ever interested in attending one of my classes. Although this is a very large room, I limit my classes to smaller than this. Oh. My laptop just told me I was connected to some random Wi-Fi. That's great. Just out of curiosity, has anyone who's been to one of my classes before? A few people. Who watches C++ Weekly? A few more. Who wants a free book? OK, I have exactly one. If someone asks like a really good question or something, then I will throw it into the audience and see if I can impel it into you. Oh, sorry. This is my C++ best practices book. I brought it because it's the book that I had to bring. I didn't actually make an intelligent decision there. OK, so then another possible title is constexpr really free? Maybe another question is, I don't really know what the title of this talk should have been. Perhaps, since I'm going last, I can take as long as I would like. It says I have 41 minutes left, but who's going to stop me? OK. We're going to play a little game. Like a lot of you raised your hands saying that you watch C++ Weekly. As such, you're probably used to this little tool called Compiler Explorer. Godbolt.org. People have heard of this. You've probably compiled an empty main or seen one compiled. Let's talk x86-64 what approximately do I expect this to compile to? All right, we'll get there in a second. XOR EAX, comma EAX, and then depends on optimization levels, one of the comments. There's another statement that needs to be put here. Ret. So something like this, right, with an optimized build. There's too many photographers in the front right now. It's making me uncomfortable. OK, so what if I do O0? What's that? Prologue, epilogue, return 0. No, we're going to get less than. We still do have to zero out EAX. Set up a stack frame, yeah, and move EAX 0, yeah. Oh, you're right, prologue and epilogue. I'm sorry. Who said that? Yeah, I apologize. Come get the book later. I corrected you, and you know, I'm sorry. Yeah, so something like this. Okay. What does this compile to? Let's do the optimized build game, I guess, maybe. Move EAX, comma 42, return, like that. All right. Now what if I do O0? Put it on the stack, maybe not, and then return. That's what I just heard. Depends on the compiler. OK, so we definitely do have to put it on the stack. Oh, look, I can paste. This is a really big stage. Where's the video cameras? Oh, are you having fun? All right. Yes. OK. So put it on the stack, maybe not was the comment. I kind of, you know what? How do I want to work this? What do you think that how am I going to load? How am I going to load 42 into EAX in O0? That's the question I'm trying to ask, perhaps. Mav EAX, comma 42, is that what you're expecting to see? Push 42. Oh, no, now we're going to get a push of 4. No, we're not going to get a. You think an O0 will load it from stack? That is the question I was going for. OK, it's not going to. So we do dutifully set up that stack variable, and then we have hard-coded 42 into EAX, return value, on line 6 of the disassembly. All right. Now, if I do Clang, this was GCC. If I do Clang in O0, do you expect something different? Are you nervous to answer? Are you awake? Does anyone need to be elbowed because they're snoring? OK, so Clang does this. It sets up like some sort of 0 first, and I'm not entirely sure why it does that. But it moves 42 into that space on the stack and then moves 42 into EAX. So they both are basically storing 42 on the stack because that's what I asked it to do on line 2 of my program. And they're both hard-coding 42 into the return value. I'm going to remove const. Do I expect anything different? This time it surely should load from stack. You're right. It is going to. Neither one of them is going to hard code the return value. I cheated, in a way. How did I cheat? Do you know the answer? I did. Why with the const did it hard code it even in O0? Because it is const is the indirect answer?
Because it's a constant expression, so it can basically go const exp.
Yeah, so there's like a rule basically that says constant integrals initialized with constant expressions are implicitly themselves constant expressions. I don't need the keyword constexpr there. It is a constant expression. I actually did an episode about this relatively recently. Okay, so what does this compile to in O0? Sorry, the timer is over that corner of the screen, so I'm like, yeah. In O0, what does this compile to? And maybe if we just want to focus just on line 7, or perhaps. Okay, so move 20 to AX and ret. Yes, that is what it is doing. Because I'm still cheating, right? I'm still initializing a const integral with a constant expression. It's therefore implicitly a constant expression. This becomes a compile time value. Now what does this look like? I just remove const from the ret val. I'm in O0. I'm going to run this program. What does this look like? Function call to, right, so function call, the result of get value is going to put it in the stack, and then the stack variable is going to get moved to ret. This is with Clang, with O0. So function call, the result is stored on the stack. And it's, if you just look at this, it's pretty easy to see how the compiler can do some of these optimizations, right? Because lines 9 and 10 look a little redundant, if you ask me. Just a tiny bit. Okay, that's about right. Now, does GCC do anything different in O0? Shorter? Is that what you said? Yeah. Where's talking? Oh, you're in the spotlight. Okay, shorter in what way? Less redundant of instructions in O0. That's often true with GCC, but there's another thing I'm getting at here that should probably surprise, I'm going to say, almost everyone. Yes? Why are we discussing O0? Because I'm going to make a point in just a second. First point, this is GCC with O0. Yeah, with O0, it often decides to go with runtime, but flipped around perhaps another way, GCC is incredibly greedy about evaluating constant expressions when it can. I did not put this into a constant expression. I didn't even make it const. And GCC said, I think I'm going to do that at compile time, even at O0, even in a debug build. How am I supposed to debug this? I don't know. It may as well be const eval. I don't know. All right. All right, constexpr. All right, I've made the thing constexpr. I think at this point, we know what it's going to do, right? It's going to evaluate this thing at compile time. It doesn't technically have to because it's not observable behavior, but it's going to, like this. All right, so what is the point I'm trying to make? That's what you were asking? The point I'm trying to make is this particular line of disassembly right here. Someone already said this, but what does this represent approximately? Storing the variable. Stack allocation. Constexpr values are still stack variables that take up stack space, at least conceptually. This is why I'm looking at O0, right? Because in O3 or O2 or O1, we know it's going to eliminate the stack usage entirely. But at O0, we can see that this is at least theoretically taking up some stack space. So, first point. Constexpr values are still stack, automatic lifetime variables that still take up stack space, at least conceptually. So with optimizations turned on, I know one of you can just write the assembly for this program, right? It's main, colon, move EAX, comma 20 ret, right? Good. Now you're all assembly language programmers. Go back and tell your coworkers this is what you learned at Code Dive. Actually, how many of you are with your coworkers right now? Oh, not as much as I expected, but fair good. OK. But we'd probably get the exact same result even without constexpr here, right? If I turned on O3, except I'm going to have maybe the function itself omitted, right? Well, the function is constexpr. That's implicitly in line, so I'm not going to. I would get the exact same result with an optimized build, even if I removed constexpr from line 6. OK. I am not looking for you to write every line of the assembly on this one. We've officially moved past that. But the question is, what does this compile to, at least conceptually? Now, I need, I've got this function called print on line 12. Let's start there. It expects a span of const ints. You have to be really careful when you say const ints, because it just sounds like constants. And on main, I have a constexpr auto data equals get data. Get data is just filling this array, 1,024 integers starting at the value 10. And so I'm going to get what? 10 through 2033. Did I do that right? Anyhow, OK. What's the assembly going to look like on line 16? What am I actually having to do on line 16? Initialize? Can be statically stored, or it can go on the stack, is what you said. But from a C++ perspective, have I created a static variable on line 16? I have not. Excuse me? An O0. I didn't specify that. OK. So I am creating a stack variable. I am asking the compiler to copy data onto the stack right here. Clang not necessarily will. But I will tell you, this is GCC with O3. You can see that line 7. What am I doing? I am copying 1,024 integers onto the local stack. And then I am passing pointers to those integers via the span wrapper to print on line 10. Does that make sense? Questions? All right. Now I have made it static. Now I'm explicitly telling the compiler, don't make me a local copy of this data. I want you to initialize this thing somewhere in the binary and then just pass pointers to it. And the generated code looks like this. And this is going to be effectively true on every compiler, because now I've explicitly told it to put the data in static storage. So at this point, it just says, give me a pointer to some static data blob that was allocated somewhere in the read-only data section of the binary, right? OK. So number 1. Potential runtime cost of constexpr, potentially expensive copies. This is something I have definitely talked about before in C++ Weekly. And I actually covered this in applied constexpr. I think the talk was called Applied Constexpr at Meeting C++ in 2017. I think it was. Anyhow, Stop using constexpr and use this instead. The point of that episode is stop using constexpr and use static constexpr. You probably mean static constexpr almost every time. And then in 3.15, I actually do a direct comparison of constexpr versus static constexpr. And then in 3.39, there's a conversation about static constexpr versus inline constexpr. You probably don't want static constexpr at namespace scope. You probably want inline constexpr because you want the linker to merge those blobs instead of loading your binary. OK. That's not even why we're here. Why am I talking about O0? Yeah, sorry. All right. What does this compile to? This is why we're here. Do you see what I have? For the rest, if you didn't hear that, the question is what optimization level? Excuse me. And for the sake of the argument here, it doesn't matter. I have a function called use. The function called use is intentionally just forward declared. By the way, if you spend a lot of time in Compiler Explorer, this is a huge help for like seeing what your code's going to actually do. If you just forward declare functions without actually defining them, then you're going to see a lot more generated code and what the compiler's having to do here. And then on line 3, I've just got a function called add. It literally does what it says on the tin. On line 6, static constexpr auto fun. What is the type of fun? So function pointer. Yeah, function pointer. And then on line 7, I call use with the function pointer, right? So the question is, what is being passed on line 7? Right there. This is a static constexpr object. It's moving offset flat colon add int comma int. Now I ask the question, is there anything missing from this assembly output? Now I'm going to see just how many of you are familiar with what level with compiling and linking and what's that? Use is void, the parameters aren't being set up. No, I'm setting up EDI, which is the pointer to the add function before calling use. It's fine. The parameters aren't being set up for the add function. Well, no, because we don't know what call is just taking a function pointer. Call is taking a function pointer. That's the point that I want to get at here. Do you know what's missing? Nobody? Hey! Did you hear him? Relocations. What is the address of a function? Is it known at compile time? I heard a confident yes. If I do like a disassembly of the linked object, then I'm going to get something more like this. These are x86 6432 things. Notice it says move 0 into EDI, but then has this thing on line 7, which is it's the relocation entry. Relocation entries. So the address of a function or really any other static data cannot be hard-coded directly into the binary. Generally speaking. We'll get into situations where it can be. This is going to be dependent on OS settings, such as like, I say at the bottom here, security settings like address randomization for where the binary is loaded, compile time link order, runtime link order. Things can vary. So the values must be runtime computed in some way, at least as an offset. You will often see stuff in the binary that might be like RIP plus 1033 or something like that. It has to do some kind of a runtime computation for what you thought was a compile time static thing. On Linux, if it's not something that can be computed with just an offset to a register, this is a call to DL relocate object. And now I will admit, I just heard someone say that like a good technical talk talks at like 20% of your knowledge level so that when people ask questions, you can answer them. I'm talking at about 90% of my knowledge level for how relocation works, okay? So if you ask deep questions here, I might not know the answer. But it gives you something else to play with when you get back home. But I'm going to try to measure these costs. The relocation table entries in the binary, functions that must be emitted, because often functions can just, like constexpr functions are not necessarily emitted into the binary, but if I create a pointer to one, then it has to admit it. The actual relocation cost itself, and potential table and data copy cost. We are going to assume GCC for simplicity. We're going to assume O3, and we're going to assume a strip binary. So only what is 100% necessary for execution. That's poorly worded. Who wrote these slides? OK, this is my example test code. I've got, 7 different constexpr functions. They do what you would expect them to do, except, mod, div, whatever, subtract, bor, so bitwise or bind for bitwise and. I needed them all to be 3 letters. I don't know. And then I have this function that is consteval on line 12. What does consteval mean? Oh, that was like 5 different answers. Wait, what? It must be evaluated at compile time is approximately what you all said. Do you say I don't know? It's also known as an immediate function if you're going to go look for it, okay? So this function is, I'm doing air quotes because I don't know. I'm sure there's some weasel words in the standard that say we can't like observe whether or not it actually was or something. I don't know. Probably Nevin. I'm just going to call you out. So this thing is going to be evaluated at compile time. All right. On line 13, I have a const array of all of the functions. And then notice on line 11, this thing takes a num. So really, I'm just creating an array of all the functions, and then I'm just taking a subset, because to me, that was the easier thing to do. Now I have a way of measuring the cost. So on line 22, I can iterate. I can say, I want to build a table of 2 functions, 3 functions, 4 functions, 6 functions, whatever, up until I see what the cost of adding each extra relocation is here. Now on line 23, I know for a fact, because I'm calling this program with 0 arguments, I know for a fact that add is always going to be called. Because if I call it with 0 arguments, I'm getting argc of 1, because on Unix, my argv of 0 is always the program's name, right? OK. So I know I'm always calling the same function, so I can remove that from the question of what are the costs here. So now I get to just measure the binary size differences in the runtime cost of the compiler and the runtime itself doing these relocations for me. I have done this as 2 different ways. I've done it this way with a non-static vals, and I have another table coming up with static vals. If I've got non-static vals, my baseline is, and this is just return add of argc, argc. Okay? So I always know which function's being called, so I've eliminated the cost of the add pretty much, but I still have an extra jump in there. Anyhow, 14,328 bytes for the actual binary, 145,118 instructions executed. I measured this with valgrind -- tool equals colgrind, okay? So if you've never used that tool, it's great for counting instructions in your code running. It is not a perfect metric of performance, but it is something that is 100% consistent because it is not sampling based. You will always get the exact same answer for the exact same code executed. All right, so if I make it a non-static table of 2 functions, the binary size goes up a fixed amount. As soon as I add in that non-static table, I find this fascinating. The binary size goes up a fixed amount. So it goes up to 14,464, but we can observe that simply adding more functions is costing me 2 to 4 cycles per function in my table. I think that's interesting. That's with a non-static table. I think slightly, let's see. So the table is always generated at compile time. It's const eval. Approximately 2 instructions to copy each function pointer onto the stack, 136-ish bytes in function relocation table. It is irrelevant if the table is explicitly constexpr or not. I measured both, exact same results. And this is, some of this is just initializing the tables. All right. Now I've made the thing static, and this is where it gets slightly more interesting. Now that it's static, I'm no longer observing the cost of copying that table. I'm now just observing the cost of actually calling the relocate function. And I can see that each extra function pointer that I want to relocate costs me exactly 13 instructions. That's neat. You're probably going, why do I care about 13 instructions? Table is still generated at compile time. It's const eval. 13 instructions to relocate each function pointer. And I did confirm that 100% of those 13 instructions is happening inside of DL relocate object. I think that's interesting. 0 copy cost happening, and the compiler is able to better compact my binary. If you didn't notice, the binary size went down a little bit. OK. So why did I even go down this road? Why do I care about 13 instructions? That's what Guy's asking. I can see it on his face.
Does anything of this apply if you compile to a bare metal executable?
I will attempt to answer that question. The question for people watching remotely was, does any of this apply if I try to compile to something bare metal? And yes, I attempt to answer that question, but I added those slides last night. Well, we'll get there, though. And I have at least an hour left to get through this talk based on my watch. All right, so I gave this talk called The Power of Compile Time Resources at CPP North in 2022. And I observed that I was seeing some bloat with very large JSON data structures compiled at compile time into tables. And Richard Smith happened to be in the audience. He commented that some of the bloat I was seeing was due to relocation tables. I have to be honest, I basically completely ignored Richard until today. I know. And then I was working on constexpr. This is my most recent experiment in scripting, embedded scripting engine for C++. It is a 100% compile time capable scripting engine. It is 100% constexpr. Its constructor is const eval. Now, when I like to talk about constexpr, I like to point out, because its constructor is const eval, it is always free to construct an object of type of the scripting engine. Because, I mean, it's const eval. 100% of that's calculated at compile time, which means it's just a mem copy, right? Whenever I want to create a new object of the engine, it's just a mem copy. Well, in episode 405, I talked about this tool called Dogbolt, the decompiler explorer. If you haven't seen that tool, it's not as refined as Godbolt, the compiler explorer. But I loaded constexpr into there, and I started looking at the disassembly from the decompiler, and I said, that's not just a mem copy. What's happening here? So I did this experiment. I have a constexpr engine that I am creating. If I don't do anything with this at all, 100% of it gets optimized away because it is const eval and it is trivially destructible and trivially copyable, so the compiler does optimize it away. But if I do O3 and I parse an empty string, I see 1.8 million instructions executed for something that's free to construct. If I parse a non-empty string, I can observe that parsing the non-empty string is only 1,000 instructions, 1,400 instructions. It's pretty efficient. And then looking into the details here, I see that, what is that? I should have put percentages. 1.6 million of 1.8 million. I have 11 minutes according to this timer. How did that happen? Are you sure? I don't think you're right. Now I'm just wasting time now. OK, so 1.6 million, what is that, like 95% or whatever, is spent in DL relocate object. I think that's interesting because I thought that it was free to construct an object of this type. It is clearly not free. Now, to be fair, 1,600 instructions, or 1.6 million instructions, how fast is your CPU? How fast is your CPU, since you asked about bare metal?
I don't know.
Oh, you just asked about bare metal? All right, fine. 3 gigahertz. Yeah, gigahertz probably. But it's a thing, because I thought it was free, but it's not. And 1.3 million of those instructions is in DL lookup symbol. All right. So runtime cost of constexpr. Point number 2, potentially expensive relocations. And then the question I have is, what does the building of that table actually look like? This is the actual disassembly of a portion. So this goes back to my example. This isn't constexpr, but this is the table of function pointers, right? So there's all these relocation entries inserted in here. And even if they can be like RIP plus whatever, some compile time known offset, it still can't do a memcopy, right? It has to actually assemble this thing, if you will, for lack of a better word, at runtime. So it's copying the addresses to these things into registers and then copying the registers onto the stack, and it's building up the stack of the things. All right. So the compiler knows what things need to be in the table, but the final values can't actually be known until runtime, so creating the table cannot be as simple as a memcopy like we would want it to be. So number 3, runtime cost of constexpr, static table with static pointers have to be built at runtime. I'm just assuming that most of you haven't considered this. Did you know this? OK. If you want to play along at home, by the way, you can go to this compiler explorer link, and this is an actual instantiation of my constexpr engine, and you can look at how much it costs to instantiate an empty one of these things. You can play with it if you want to yourself. Although Compiler Explorer is notoriously bad on cell phones, so you'll probably want to just save that URL and load it later. All right, my conclusions here. constexpr does not change object lifetime. Be aware of that. Be aware of potentially expensive copies of data. This is a real point. I have, in fact, personally measured a serious performance regression because I made something constexpr but left it on the stack instead of making it static. Relocations are potentially expensive, but they should be paid only once per runtime, I think, during execution. And compile time tables with compile time pointers still have to be pieced together at runtime because of the relocated assets. So this should not stop you from using constexpr. I just thought this was an interesting exercise. Embedded and static binaries that are not relocatable can limit or eliminate the impact. I attempted to put this together. What architecture did I compile for here? Not ARM. What's that? AVR. AVR is so much more fun than ARM. Come on. All right, so this is AVR, which is a 8-bit platform with 16-bit addressing, right? Like all good processors are. So those are my functions. And my main here, as far as I can tell, it is actually basically able to hard code this into the linker, into the assembly, what the locations of this would be, because it knows the entry point into this executable, and then it's able to just load pointers into that compile time known entry points for the table. So if you're doing embedded stuff, definitely don't worry about relocation entries, all right? You can mitigate those problems. All right. So you are still not executing user code at runtime. constexpr does not affect object lifetime, but so you probably actually want static or inline. constexpr pointers have to be relocated. Don't forget that. This comes up. This came up in my first example with the compile time JSON stuff because I had like spans of things, and there's a lot of relocation entries there. Be aware of what you're asking your compiler and runtime to do. Some portion of relocations are string compare, interestingly, when it's actually looking up the name of the symbol at runtime. So hypothetically, if you have very large mangled names, that can actually slow down your relocations as well. And how easy is it to get very large symbol names in C++? All right. And if you want to play along at home, again, object dump -dr, capital C, capital M, Intel is my recommended way of getting the relocation entries inserted into the disassembly of your binary if you want to play with it yourself. All right. So now, like me, you know too much. And now I have to say, check out constexpr, my scripting engine, with 0 runtime cost, because I was like, there's something happening there, and I didn't want there to be. All right, so this is the runtime cost of using constexpr. You can contact me if you've got any questions, and I don't know if you want to contact me about anything. MC is coming on stage.
Yes, I am. Jason, thank you so much for this very conversational and inspirational talk. You have been able to ask questions. If you haven't been able so far, now it's time. One over there and the second question over there, please.
All right. Oh.
One over there. Let's start with that one there. Can you still raise your hand? Make yourself visible. Thank you. Just for the mic.
You really don't need the mic, but whatever.
Okay.
Well, no, go ahead and use it now that you have it.
I don't think it's work. Oh, okay. So I think there's a difference that you have to kind of, I think that you missed here, which is that you have link time relocations and runtime relocations.
Right.
So in case of those LIAs that you saw, I think that was actually an optimization by the compiler. Because if the LIA doesn't cause a runtime relocation, that's a link time relocation.
Right.
So then the program can be like copy and write it, essentially. So when you start it again, it doesn't have to do the relocation again. It just decided that, oh, I will just do a bunch of LIAs and then copy that into your memory. So
interestingly, you're right, and yes. So okay. So your functions are going to be laid out, and let's take stock specifically about function pointers. Your functions are going to be laid out in whatever order the compiler or the linker decides to put them actually in the binary, right? So you need pointers to those things. And even in the case where the compiler can optimize it, or the linker can optimize it, and remove the calls to the DL relocate object, it still has to have an offset, right? So you can eliminate the runtime relocation cost up to a point, but you still cannot eliminate the runtime building of the table of function pointers, because it still has to take current instruction pointer plus whatever offset, and load that into a runtime table based on what the instruction pointer offset happened to be.
No, but the compiler can also emit absolute address to function at sub blah 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 in a table in the data section.
I don't think it can absolute address.
Yeah, because that's a relocation. That's a runtime relocation.
Oh, okay. You're
So
saying
it can do that, but it didn't, I think, because it wants to basically make it easier to copy and write the binary. But we can talk also offline more if you want. I
don't think on any modern operating system it can hard code a specific address. It always has to be an offset because it doesn't know what location the operating system is going to load the binary into. Oh, they cut you off.
No, I didn't answer yet. You can. That's what the relocation is for. That's called an absolute relocation, and that will emit, like in the ELF file, it will emit an absolute relocation that says this is the offset to the function. That's what the linker knows, and then it needs to add the base address of the binary, which is randomized.
Okay,
So
but it still has to add the base address.
Yeah.
Yeah. Okay, we're saying the same thing. So something has to happen at runtime. Something has to happen at runtime.
Yes.
Okay.
One question over there, please. That person in glasses, thank you.
Where?
Hey. Hello, Jason.
Oh. Now, why'd they give you a mic? No.
Don't worry. Have you tried on Windows?
No.
Because
No,
I think what you're hurting is the one thing that Microsoft got correct, which is that symbols are not relocatable or variable by default, so they don't need to be like PLT blah 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 bullshit.
But I thought Windows could still do randomized.
Yeah, but it should just be like relative to instruction pointer rather than have like the relocation code.
Well, yes, but still like what they said. But still, if you have a table of these pointers, something has to be done at runtime to do the offsets to the function pointers.
Right.
Yes.
You can probably disable, like, FPy is an option technically. It might be the default, but you can probably disable all that if you're a crazy person that really don't want to pay for it.
The only way I could get it to completely remove it was in the AVR code where I said, you know the entry point of this binary, and then it was able to hard code the rest of it. That's the only time I was able to get it to hard code the whole thing.
Okay. I think there's might be like an no pick or whatever from like pre-relocatable.
Pre-relocatable.
Yeah, not recommended by any means, right?
Why am I still holding this? Okay. Oh, there's a question. Just yell real loud.
Right. So on my box, I'm getting rip relative addresses to the entry point to the function.
Okay.
Now, I guess you can get that on Linux. It's not just Windows.
Rip relative address. Yes. Right. So you might not get a call to relocate object, but you still have to do the rip plus something. That's what I keep coming back to. It's not like it cannot build the table of function pointers at compile time. It can't. Yes, I think I'm being like cut off. I think. No?
Not by me.
Oh, so I still have as long as well, the screen keeps changing. Yeah, so even if it doesn't do a call to an operator or to a runtime linker code, like if I had a table of function pointers that was consteval and I thought that it was making this thing at compile time, it can't.
This is you, Jason, not being cut off, on the contrary.
All right, I'm out of here. Thank you.